Take a look at this.
See the universe through a brand new set of eyes. One moment after the other, everything is new. Why not just ask why? I'll live each day with wonder. See the universe through a brand new set of eyes. One moment after the other, everything is new. Why not just ask why?
To understand why this Escher waterfall can't be real, why it must be a beautiful fake, we need to understand energy better. Here comes one of the deepest, most pervasive, and most useful ideas in all of science. It's called the law of energy conservation. The total energy of a closed system remains constant. We'll apply this law to the Escher waterfall at the end of this video. Symbolically, delta capital E sub CS, closed system, equals 0. The change in the total energy of a closed system is 0. That's what the word conservation means in physics. A quantity is conserved when the total amount of it doesn't change, when something can be neither created nor destroyed. The challenge for us now is to make sure that we understand what capital E, total energy, means, and what a closed system is. In Radical Physics Episode 12, RP12, we used the idea of work to learn about 3 very basic forms of energy. We learned their symbols and their formulas. Kinetic energy, capital K, is the energy of macroscopic, that is, large-scale motion, and is defined as 1/2 mv squared. Thermal energy, capital T, is the energy of haphazard microscopic motion, and is defined as the sum of random molecular kinetic energies. Potential energy, capital U, is the energy of relative position. It comes in many types, including local gravitational potential energy, capital U sub G, which is defined as mgh. Now we can define capital E as the total energy, kinetic, thermal, and potential. Capital E is defined as K plus T plus U. But energy of what? Capital E represents the energy of all the things that we're considering in a given situation. Those things are called the system. A system in physics is a set of things that may affect each other. And a closed system is a set of things that is not affected by other things. This sounds more complicated than it really is. By looking at a few examples, you will come to understand what a closed system is. Just be patient. As a first example, let's use the law of energy conservation to find the speed of an object, Bart Simpson, that falls from rest through a distance of 10 meters. 10 meters is a long way when you're falling. It's about 33 feet. That's the height of a 3-story building. If you fall from the roof of a 3-story building, you're going to be going quite fast when you reach the ground. Unless you land on something very soft, you're gonna get hurt. Fortunately, Bart won't feel a thing. Given h equals 10 meters, g equals 10 meters per second, find v equals what just before impact? Formulas. What formulas, what laws and definitions of physics should we use to solve this problem? This is often the hardest part of a physics problem. What approach should we use? Here, since we're learning about energy conservation, that would seem to be the obvious approach. But why not use good old kinematics? Since we know the distance of travel and the acceleration, the equations of kinematics should allow us to find speed. And they do. However, here's a little problem-solving tip that often proves useful. When you want to find speed, first consider energy conservation. This tip works because speed appears so clearly in the kinetic energy formula. So if a problem involves the energy of motion, as this one does, the easiest approach to finding speed will probably be energy conservation. Here goes. Our formulas are first delta E sub Cs equals 0, where E sub Cs is defined as K plus T plus U. K is defined as 1/2 mv squared, and U sub G is mgh. The closed system here consists of Bart and the Earth. No other objects are involved. You might argue that air molecules are involved because Bart constantly runs into air molecules as he falls. But this effect is tiny for small objects that move fairly slowly through the air. So we're going to neglect air molecules. We say that air resistance is negligible in problems like this. You might wonder about the moon or sun. Their gravity does act both on Bart and on the Earth. However, gravity is a special force that acts in the same way on both Bart and the Earth. The end result is not that lunar and solar gravity are negligibly small, but that they are inconsequential. With practice, you will learn to identify cases in which forces are negligible, like air resistance, and cases in which forces are inconsequential, like the gravity of moon and sun. Here, there is no significant outside force acting on Bart and the Earth, so the system is closed. A system of masses is closed when no significant external force acts. Since this system of Earth and falling object is closed, we can apply the law of energy conservation. But what about that delta? How do we interpret this symbol for change? We must remember that it actually means difference in energy, final energy minus initial energy. So here is a key point when using any conservation law. We must identify both the initial state and final state of the system. Energy is always conserved, but to apply a conservation law, we need to choose the initial and final situations wisely. Look at what we want to find in this problem. The speed of Bart just before he hits the ground. So certainly that should be either the initial or final situation. To identify the other situation, look for a state of the system that is simple to describe. I hope you see that this other simple state exists just as Bart begins to fall. At that time, Bart has no kinetic energy, so his energy is particularly easy to describe. So we have chosen the initial situation to be as the object starts to fall, and the final situation to be as the object reaches the ground. Now we're ready to apply the law of energy conservation to Bart's final speed just before impact. Delta E sub Cs equals 0 implies E final minus E initial equals 0. A little algebra gives E final equals E initial, and substitutions from the key forms of energy give K sub F plus T sub F plus U sub F equals K sub I plus T sub I plus U sub I. The two T values, the initial and final thermal energies, are unknown, but they're the same unknown because no thermal energy is added or taken away here. So we can just subtract that identical thermal energy from both sides of the equation. K sub F plus U sub F now equals K sub I plus U sub I. Since Bart is initially at rest, he has no K sub I. And since Bart is finally at virtually no height, he has no U sub F. So K sub F plus 0 equals 0 plus U sub I. Now we can substitute in the definitions of kinetic and potential energies. 1/2 mv squared equals mgh. A little algebra gives us V equals the square root of 2gh. Energy conservation has told us that a falling object's speed of impact depends on the square root of its initial height. So if you want a falling object to hit with twice as much speed, forgive me, Bart, you've got to drop it from 4 times as high. 3 times as much speed, 9 times as high. This is something that kinematics could have told us as well, but look at how quickly energy conservation revealed it. Now, finally, let's plug in numbers and units for this particular problem. V equals the square root of 2 times 10 meters per second squared times 10 meters equals the square root of 200 meters squared per second squared equals 14 meters per second. That's over 30 miles per hour. You don't ever want to hit the ground going that fast. We should do other examples like this to get accustomed to using the law of energy conservation. Here's one example based on a remarkable movie action scene. And here's another that uses energy conservation to predict the theoretical limit on the pole vault record. Energy conservation allows some wonderful insights. Consider the simple act of turning our first example around. Instead of dropping an object, suppose we ask how fast an upward bound object must go to reach a height of 10 meters. The answer is the same, 14 meters per second. Energy is the key. As an object falls from a height of 10 meters, its potential energy turns into the kinetic energy of something moving at 14 meters per second. And as an object rises, the kinetic energy of a 14 meter per second speed turns into the potential energy of 10 meters of height. If our choice of initial or final situation had been different, the law of energy conservation would still have applied, but using it would not have been so fruitful. For example, suppose we had chosen the final situation to be 1 second later, 1 second after the object hits the ground. Where's the energy gone? Delta E sub Cs equals 0. Is this a closed system? Yes, the falling object and the Earth are not affected by any significant external force. So, E final equals E initial. K sub F plus T sub F plus U sub F equals K sub I plus T sub I plus U sub I. 0 plus T sub F plus 0 equals 0 plus T sub I plus U sub I. T sub F minus T sub I equals U sub I. Delta T equals mgh. The initial potential energy of the elevated object has become the increased thermal energy of the object as it lies on the ground. The fallen object is warmer than it used to be, as is the ground that hit it. If we understood key molecular properties of the object and the ground, we could actually predict how much warmer each of them has become. But the important point is that energy is conserved, and we note that the final state of this energy is thermal. We will understand later in radical physics why nature so favors thermal energy in all energy transformations. Other examples of energy conservation are all around us. Everything that has ever happened, except perhaps the Big Bang creation of the universe itself, has demonstrated energy conservation. To find unlimited examples that demonstrate energy conservation, we just have to open our eyes. It's finding one counterexample that would be fantastic. The Escher waterfall that we saw at the start of this video messes with our sense of up and down. But more important, it messes with our physical intuition that energy is conserved. The kinetic energy of the water and of the water wheel appears out of nowhere. Maybe it started as potential energy when water was first poured into the trough, but that potential energy never gets depleted. It keeps turning into kinetic energy and into thermal energy as the same water keeps flowing round and round. The water is always getting warmer as it rubs against the trough and against the water wheel. Thermal energy keeps getting produced, but kinetic and potential energy never get depleted. In this closed system, energy is being created, not conserved, So we know that the Escher waterfall is a beautiful fake. The total energy of a closed system is conserved. This is one of the very deepest laws of nature. We have only scratched the surface of its utility here, but you can trust that we will come back to it again and again in radical physics. If you awaken one day to find a closed system in which energy is not conserved, in which total energy is either created or destroyed, you might as well believe that you've been transported to a different universe. That's how fundamental the law of energy conservation is.
When you understand the laws of physics, Penny, anything is possible.